Potential for a sec. Let's talk about what water potential is. So the story is always the same. You have a beaker or a container of any sorts, and there's a cylinder, and all you're trying to figure out is where is the water potential greater, inside or outside? Wherever it's greater, it's going to go from there to wherever it's less. Make sense? And we know that the more salt you have, the lower your water potential. Pure water has a water potential of 0, exactly. So we know that if this side has a lot of stuff, whether it's a salt or a sugar, it's going to be dropping its water potential, correct? If the outside has a lot of stuff in it, that's going to drop its water potential. And the question we have is, whose water potential has been dropped more to determine which way the water is going to flow? Because it goes from high water potential to low water potential. Does that make sense? Like the big picture, right? So all we do is, whenever we add something to the water, we drop its water potential. Are you with me so far? All right. The other reason the water moves is because of physical pressure. So no matter what solution I have in here, even if there's stuff dissolved in it, if I push on it, if there's physical pressure, that's going to override the osmotic pressure, correct? I mean, I could put like a bunch of stuff in here, and water should be moving in. But if there is actual physical pressure, that's going to override everything, right? I'm forcing it. And that's why the equation is water potential, which is letter psi, is equal to psi s, which is the potential, water potential due to these substances, right? The solute potential, right? Plus, you got to take in psi p, the actual push. Makes sense, yeah? Questions so far?
Yeah.
The whole thing makes sense? All right. This is how I like to solve these equations. So the first thing I like to do is I like to write down every variable that I have. So I've got two situations. I've got my variable. I've got inside cell. And then I got outside of the cell. And I got something like this. Okay. So now I just start listing all my variables. I've got psi, so I just write psi. I got psi s, solute potential, yeah? And I got psi p. What other variables are there? There's I, right? In this whole story, there's I. There's concentration, C, in moles. What else did he think about? There's R. And then my last one is temperature in degrees Kelvin. That's it, right? Okay. Some of these I don't have to worry about. I don't have to worry about. Because if it's a sugar, I is 1. And if it's something that ionizes like a salt, then I is 2. So it's going to be probably 1 or 2. But I don't have to worry about this. I got this. I got this from the story, from the narrative. What else do I got that's a given? This one right here, R. R is a constant. It's always 0.0831. That's right down over here. Here it is, 0.0831. So these two are done, and this one I got. It's either 1 or 2. 1, it's not a half. I should just probably write it down. 1 or 2. So 1 or 2. This one is always going to be the same. 1 or 2. Most probably, right? So I just didn't figure the other ones. Okay, so if we look at like number 7, let's figure it out together. So at 20 degrees Celsius, where does that go? That's my temperature. 20 degrees, do I just write 20 degrees? What do I write? 293, why? Because to go to Kelvin, you just add 273 to whatever you have, right? So it's 273 plus 20, so it's Celsius plus 273, correct? So I'm going to write 293, and that says, is that inside or outside? At 20 degrees, a cell containing, so is that inside or outside? Inside. So inside, you said, I go inside, and we said 293 K. What's the outside? It doesn't tell me. It says, at 20 degrees, the cell containing 0.6 molar glucose is in equilibrium. So, is this in equilibrium temperature-wise with the room? Will this be the same temperature as the room? Yeah, of course. It's not a thermos. It's not insulated. Should be, right? Is this book the same temperature as the room? Yeah, it's been sitting here for like a day. How else is it going to be? Yes, it is. So if you're in an environment in equilibrium with it, you're going to be the same temperature. Unless if you're insulated or your refrigerator plugged in, right? You follow on this? Are you the same temperature as the room? No, of course not, because you're a living thing. You have your metabolism, right? But is the desk the temperature of the room if no one is touching it? Yeah, in the morning it's temperature of the room. Okay, so the cell is sitting there, and it's in equilibrium with the room. So I've got this number down. What other number do I have down? What else is in equilibrium? If I'm a cell sitting inside a container, what else is equal? We said temperature is equal, same temp. What else is equal? Yes. Good job. Yeah. The overall movement of water. So water is moving out and moving in the same. We can't say pressure, but we can say water potential. Water potential is caused by pressure, but it's also caused by solid potential. But we know that whatever it is, it's in equilibrium, meaning it's going in and coming out at the same rate, correct? Which of these variables would tell me that they're the same? Which of these, are these the same? These the same? Which ones are the same? Yeah, you're right, the top one. The overall is the same. So I'm going to put it equal over here, because I have that information.
She just needs to get her belongings and we're going.
Okay, so I know. So these two are equal. Do I have concentrations? Yes. It says the cell is 0.6 molar. And it says the outside is, what does number 7 say? It's on your computers. 0.5 molar, correct? I got that down. That's why I like this table. I don't have to think too much. I'll have to just fill in. I know these are equal. I got this. I'm like almost done. And what do they want? What is the cell's psi p? So what is this? This is what they want. So I put a question mark. Now, do I know outside the cell psi p? So I go back here. Surrounding solution in an open container. The container has no pressure on it. It's open. The cell is not. It's like a balloon, maybe under pressure, correct? The balloon could pop. Is that true? Yes. Is the room gonna pop? No, because the room is not containing anything, right? There's no pressure on it. Do you follow the thinking? So I know that psi p for the outside is how much? How much is the pressure potential for the beaker? Good job, 0. You're right. That's 0. So I don't have much left that I have to figure out. I just need this. So how am I going to go about figuring out my psi p for the inside? So what do I know? I know these two are the same, inside and outside, right? I could say, since inside, I like doing this inside-outside thing because it stops me from being confused. Here's what I could say. I could say this, which I already did over here. Yes? You could say psi is psi for inside and outside. You could say that. But you could also say psi s plus psi p is equal to psi s plus psi p. You could say that. Since psi is psi s plus psi p, you could say that. Are you with me so far? It all makes sense? Okay, and I know outside, what is psi p? 0. So I already know that this is 0. So that tells me if I figure psi s, that would equal to, of the outside, that would equal these two numbers. Now what I want is this is my target right here. Does everybody understand where we're at? Okay, so I'm going to stop, and I'm going to ask you, I'm going to pick someone to come and figure out. What's Kaylee going to figure out? What's the first thing she's going to do? Psi s or psi p for the outside? Psi s. Which is the same. Not the same though. Psi p is 0 already. So, Kaylee, you're going to write psi s. Psi is like the Poseidon, yep. Equals I, little letter I, and then C or T uppercase. All right, which is equal to, okay, what is I? It's sugar. So what is I? What is I? 1. So it's put in parentheses, it's negative, I'm sorry. It's negative, correct? Negative ICRT. There's a negative sign in front of the I. Yep. So it's equal to negative. And then parentheses, 1. That's I, correct? Okay, close parentheses. Times C. What is C for the outside? 0.5. In parentheses, 0.5. Okay. Times, parentheses, what is R? 0.0831. Okay, good, 0.0831. Wow, okay. Times, I like how you save ink by writing really small so we don't have to waste it. That's good. And T is, I'm just kidding. T is 293. 293. Any smaller on that ink will last us a whole life. Which is good. All right, who can help us with the calculator part? Somebody take it out. Take initiative. 1 times 0.5 times point. We're missing a 0 there. It's 0.0831.
That's negative 12.2.
Nice. So equals
No, that's mine. That was mine.
negative 12.2.
That's not that.
Okay.
That was mine.
So if psi s is negative 12.2, what do we know? We know that psi, this is for the outside by the way. Outside the cell, correct? We know psi equals psi s in that case. Correct? Which is equal to negative 12.2. But we also know that for, I'll just do this side. We know for inside, from our equation, from our table, we know that in and out, psi is the same. So now we can go inside the cell and say, let's help you a little bit. We can say that psi inside the cell equals psi s plus, here's the golden one we want. We want this guy, psi p, right? You follow? So we know psi is negative 12.2 equals, do we know psi s for inside? Would you not? Do we know psi s for inside? Not yet, we will. Equals, this thing is going to be negative ICRT, correct? Plus psi p. And then we're going to solve, we're going to get this fixed. So that's our next step. All right. So what is negative ICRT for inside? So we just have to figure it out. It's going to be, so write psi s, same thing as before, equals negative ICRT. And just write the words inside, like somewhere like on the side to the left there. So we know that's inside. Good job. All right, somebody tell me, what is I for inside the cell? 1. I see you showing 1. 1 times, what was our concentration inside? 0.6. Okay, times, I need R. What is R? It's always the same, right?
Yeah.
Okay, 0.0831. There's a 0 after the decimal, it's 0.08. That's it. Cool. Good catch. Okay, times the temperature is 293. Somebody take out your calculator, tell us what this number is.
That is 14.6.
14.6, nice. Which is equal to negative 14.6. Beautiful. So now we know that this number, negative 12.2, equals, you can just rewrite it, negative 14.6 plus psi p. That's the thing we wanted all along. All right, can we solve this simple equation? Yes. We can add 14.6 to both sides, yes? Okay, so negative 12.2,
So it freely moves wherever it wants.
you know how to do it from this point? Yep, exactly. You got it. So that's going to be 2.4 equals 0 plus, equals psi p, you're right. So that's our answer. 2.4. 2.4 bars. You can write the unit as bars, right? Is that what you got? Yeah, that's what you got. So that means that the physical push. Awesome, thank you. Good job. Big applause for Kelly. Very brave. Okay, so that means that inside the cell there was a push, physical push, equal to 2.4 bars. So if we think about this situation, like understanding it is kind of important. Where is there more stuff dissolved, inside or outside the cell? What's my concentration outside? 0.6 molar. What's my concentration inside? 0.5 molar. Which way should the water move? Which way would you expect it? You'd expect it to go from where it's more to less, right? So it should go like this. Right? The water is more pure here. So over here, there's going to be more solute and a lower number because there's more solute for water potential, correct? And in addition, the cell itself is under pressure. So you know the water is going to be going out pretty fast. Is that correct? You follow me on this? So there's two things working to push the water out of the cell. There is the solute difference, plus there is the physical pressure. Did that all make sense? Okay, we're done with that one. That was the law.